People say learning Python takes months. They are wrong. The truth follows the Pareto principle, also known as the 80-20 rule. You only need the right 20% of Python to build most of the software you actually care about. Welcome to the Python Fast Track. In this tutorial, I have taken around 35 core Python concepts, from simple variables all the way to object-oriented programming and APIs. Instead of a boring checklist of topics, I have organized everything into 6 real-world projects. And these 6 projects will quietly teach you the most important 20% of Python along the way. By the end, you will have all the 6 projects uploaded to your GitHub, giving you an instant portfolio to showcase your skill. I have put the complete source code and a printable PDF cheat sheet in the description below, so sit back, relax, and focus on the logic. Now I know that you want to start building this app immediately, but every artist needs a canvas and every engineer needs a workshop. Before we write a single line of code, we need to install 2 things: Python, which is the engine that runs our code, and PyCharm, which is the professional tool we will use to write it. It takes less than 5 minutes. Let's get set up. First, let's check if Python is already installed on your machine. Open Windows PowerShell and type python --version. If Python is installed, you will see the version number. But now, as we don't see the version number, that means Python is not installed in this system. So let's go for the next step. Open your browser and go to python.org/downloads. From there, download Python. Go to the installer file location, run the installer. Stop here. This is the most important step. You must check the box that says add python.exe to path. If you miss this, your computer won't be able to find Python later. Check the box, then click Install Now. Once the setup is successful, close the installer. Now watch this. If I go back to my original PowerShell window and type python-version, it still fails. Many beginners get stuck here and think the installation broke. But here is the secret. The terminal doesn't know about the new installation yet. You must close the old window and open a fresh PowerShell. This forces Windows to reload your settings. Now try python-version, and there it is. We can see that Python 3.14.1 is installed. That's how you can install Python in your system. Let's verify if it works. Type Python to enter the shell. Then type print hello Python. There is your output. The engine is running smoothly. Now that we have the engine, we need a professional dashboard to drive it. We are going to use PyCharm. I simply find it to be the most user-friendly tool. Head to jetbrains.com/PyCharm and click download. You will notice it is now a unified product. This means you don't need to hunt for a separate community edition installer anymore. Just click the download button. Run the installer. I recommend checking all the boxes here. This ensures your shortcuts are created and your open folder options are ready. Click next, then install. Once finished, open PyCharm. Since this is a fresh install, select skip import. Now let's create a new script. PyCharm automatically gives us a sample script. You can see it as a pre-written function. Let's test our setup. Click the green play button in the top right corner. In the console below, you should see Hi PyCharm. This confirms that PyCharm is successfully talking to Python. Your workshop is ready. Now let's get to the fun part. Let's build our first app, the age calculator.
It asks for your name and age, then tells you the exact year you will turn 100. Along the way, we will cover variables, input, casting, printing, math, fstring, and comments. Open PyCharm and create a new project. Make sure Create a welcome script is unchecked. We want a blank slate. We will use project v&v as interpreter type. This tells PyCharm to create a clean, separate virtual environment for this project so it does not mess with other codes. Just hit create. Right-click your project folder. Create a new Python file and name it age_calculator. Let's start with the comments. Comments are nodes in your code that Python ignores. They help explain what your program does. Here I have used both single-line comments with hash symbol and a multi-line string with Python triple quotes. So this triple quoted block is often used as documentation in Python. Now we need data. Let's store the user's name and age in variable. A variable is just a container for data. Start with the name. PyCharm helps us here. See how it suggests the code before I finish typing. That's one of the benefits of using an IDE. In Python, we use the input function to ask the user a question, and we store their answer in a variable. Next, ask for their age. But wait, Python treats all inputs as text string. We can't do math with text, so wrap the input in int function to convert it into a number. Here we will use this input function to get the data and int function to convert age into a number. Notice how we cast age into an integer using int. Without this, Python would treat it as a text. Now the easy part. We create a variable years left and just subtract age from 100. We will set current year to 2025. Don't follow the suggestion of the IDE always, so we type 2025 here. Now here is a way to make Python pull this date automatically from your computer clock. But let's keep it simple for your first script. To find the exact year, we create a variable turn 100 year. Take the current year 2025 and add the years left. We will save this in turn 100 year. Finally, let's print the result. You can use the method suggesting here, but we will use fstring to combine text and variables in one neat message. Fstring makes formatting easy, just put variables into curly braces. Let's test it. Right click and hit run. I'll type name John Smith and age 25. So that means John Smith will turn 100 in the year 2100. That's it, your first Python app. You learned variables, input, casting, printing, math, fstring, and comments, all wrapped into a fun age calculator.
Let's build your first mini casino game. The computer picks a secret number and you keep guessing until you win. This one teaches you library, loops, logic, and debugging. Open up the project we used last time. You can find it in the recent project list or just click open and select your folder. Once it loads, right-click the project folder, create a new Python file, name it guess number, and now we have a fresh blank slate. First, we need to give Python a brain. We import random module, a toolbox Python gives you. This is like a plugin that lets the computer roll dice. We create a variable called secret number. We ask random to pick an integer between 1 and 10. You can change this to 100 later if you want to make it impossible. Now, the game needs to keep running until the user wins. We use a while loop. This line literally translates to while the user's guess number is not the secret number, keep playing. Inside the loop, we ask for input. Remember to wrap it in int function because input is always text, but we need a number to do the math. Now for the logic. If the guess number matches with the secret number, we print you own. We break the while loop. But if they are wrong, we need to help them. We use elif, which means else if, to check if it was too high, or for anything else we just say too low. Let's run it. I pick 3, too high. I pick 1, too low. I pick 2, you own. The loop breaks and the game ends. Now let's see the brain of the loop. Click the red dot next to the while line and hit debug.
This freezes time right before the loop starts. See this thread and variable panel. It shows you the variable secret number is 9 before the game even asks you. You can also see the value in the script also during debugging. Guess number is currently 0. Python asks a boolean question. Is 0 different from 9? You can evaluate the expression by right click, then evaluate, and the answer is true. Because it's true, we are allowed to go inside. Let's click step over. It takes us to the next line. I'll type 3. Now watch. The code check the if logic. Evaluate the expression. It is false. If we step over again, it takes us to the else condition. This is also false. So we ended up in else logic, that is too low. This time click resume program. Check again with number 10. This time it stuck in else logic and shows too high. Now I type 9. This time it hits the if logic and the logic is true. It makes us inside if block, print you own and break the while loop. This is how a while loop thinks. It's just a gatekeeper checking for true or false. And we saw the power of debugger. It lets you see inside your program, and this is how real developer understands what's happening. You just built your first interactive game and you used library, loops, logic and debugging.
Now let's take that exact same logic and turn it into a fun visual game using Python's turtle module. First, copy guess number script by pressing Ctrl C and paste it with Ctrl V. Rename it like Casino Game GUI. Split your screen to keep the old script and this new one side by side so we can compare the changes. We are not going to change anything about the logic, we are just giving it a skin. Start by importing Turtle. While it's often used for drawing, it has a hidden power. It can create simple graphical user interface or GUIs without us needing to learn complex window logic yet. Let's prepare the canvas first. We use turtle.hideTurtle and pan up because we don't want to draw lines. We just want to display text. For turtle.goto, we use 0 for x-axis and 150 for y-axis. This moves the text higher so that pop-up window doesn't cover it. Now, look at the loop we built earlier. Instead of the standard input function, we are going to use the turtle.num input. This command triggers a professional looking pop-up box that asks for a number. Put the title casino game and the prompt guess a number between 1 and 10. For minimum value we will use 1, for maximum value we will use 10. Since num input returns a floating point number, we are still using that int function for casting, just like before. Next, add turtle.clear inside the loop to remove the previous message before writing a new one. Notice how we can still use our while loop logic. The program will keep showing this pop-up as long as the guess is incorrect. Now, we check the guess exactly the same way we did before. Instead of using print, we use turtle.write. This draws the results too high, too low, or you own directly onto the window screen. Run the code. See that? A real window appeared. You didn't just write a script, you built an interactive application. Try entering 1 and clicking OK, it shows too low. Try other values. If you guess 6 and the window closes immediately, that means you own, but we have two small issues. The font is too small and the window disappears too fast. Let's fix it. To fix the font, go inside the write function and adjust the align and font parameter. Finally, end the program with turtle.done. This keeps the window open even after you win so that you can celebrate your victory. And that's it. You just turned a simple console game into a visual game without learning anything new. Same variable, same loop, same condition, just a new interface. Now, let's learn to save data permanently and handle list of items by building a task manager. We will cover tuple, list, set, list comprehensions, for loop, and professional file handling. Let's dive in. We store data inside variables. But variables have a big weakness. They live in your computer's RAM. That means the moment you close your program, the data is gone forever. Today, we fix that. We will write a script that saves your to-do list to a text file so it survives a system restart. We don't need to create a whole new project for this. We can just add a script to our existing workspace in PyCharm. Go to your project folder on the left. Right-click, go to New and select or create a Python file. Let's name this Task Manager. Now we have a fresh blank script ready to go. First, we need a place to hold our data. In Python, we have different types of containers. A tuple is a list that cannot be changed. This is great for settings. See this parenthesis? That tells Python, don't let anyone change this. But for actual tasks, we need to add and remove things. For that, we usually use a list with square brackets. However, instead of starting with an empty list, let's see if we have any saved data first. To read a file, we use a try and except block, just in case the file doesn't exist yet, like on the very first one. Inside the try block, we use this with keyword. This with statement is a context manager. It's a professional way to code because it automatically closes the file for us when we are done. No more memory leaks. We will read all the lines into a variable called raw data. Here is a pro tip. When you read from a text file, Python keeps the invisible new line character at the end of every line. It looks messy. We could write a long loop to fix that, or we can just use a list comprehension. Look at that syntax. It's saying strip the white space from every line inside raw data. It does a whole loop in one single line of code. If the file is not found, that is except block, we just set task to an empty list. Now let's ask the user for a new task. But what if the user types the same thing 2 times? For example, buy milk and buy milk. So buy milk is already on the list and we don't want duplicates. We could write complex logic to check, or we can just use a set. A set is a collection that cannot have duplicates. By converting our list to a set, Python automatically deletes any double entries for us. Then we turn it back into a list. We have our updated list. Now we must save it or we lose it. We use with again, but this time in W mode for write. Be careful. Write mode deletes the old file contents and creates a fresh version. We loop through our tasks and write them down, adding a manual \n so each task gets its own line. Finally, let's show the user what is on their agenda. We use a for loop. This loop grabs the first item, print it, then grabs the next until it hits the end. Let's run it. At first, we don't see any text file here. Also, current task loaded is 0. For the first run, I will add learn Python. Run it. We see our updated to-do list. And also we see that a new text file has been created. If we check the content of the text file, we see learn Python is here. Now run it again. This time we see current task loaded is 1. I will add go to gym, see the updated list and the updated text file. For third run, I will add go to gym again. Look at the output. The set caught the duplicate, go to gym. So it was not included for second time. You just build a program that has long-term memory. You learned about tuple, list, set, list comprehension, for loop, and professional file handling. In this session, we are going to build a Python-powered car simulator complete with a GPS system, a trip computer, and a smooth engine startup sequence. And while we are cruising through this digital highway, we are also going to master one of the most important and confusing concepts in Python: if name equals main. So buckle up, adjust your mirrors, and let's take this code for a spin. Let's open up our first file, car-dashboard.py. We will have 5 steps for this file: the data for dictionary, function without argument, we will use that to start the engine. Another type of function with argument and return, we will use it for trip computer. Then main program for the driving logic and the ignition key. Instead of writing top to bottom, we will work on several parts simultaneously from the very beginning. I found this style always helps to write big code with better understanding and less error. Before we start the engine, every car needs a navigation system. Here, our journey begins with the GPS favorites. We need to store the destination our car knows. In Python, we have different types of containers. This time, we will use dictionary. Now, why a dictionary, not a list? A list is like a grocery receipt. You have to read line by line to find what you need. Item 1, item 2, item 3. And a dictionary is like a vending machine. You don't look at every snake. You just type the code or the key, say A1, and you instantly get the specific snack. That is the value. In the same way, you don't want to type in GPS coordinator or distance every time you drive. In Python, you give a key for the location name and you get a value. Here in our case, that value is the distance. Now come to section 4 and loop through the dictionary keys. Here, place is the key and we are using that key to call the value from the dictionary. To make it look nice, let's add an emoji. Here, we created a dictionary in section 1 and loop through the dictionary in section 4. Run the file, we can see the keys and the values printed here. Now that our GPS is loaded, it's time to bring the car to life. To start the engine, we normally need to inject the fuel, spark the plugs, and then the engine starts. Run it and we see that engine is started. If we want to start the engine again, we need to use this block of codes again. So if we write that code manually every time, it gets messy. In real life, do we inject fuel or spark the plug every time? No, we just want to press one button and have the car do the rest. In Python, we use def to define customs command into a function. Let's create a function called start engine. Now look at this red squiggly line. If you hover the mouse over it, it gives you a hint. Indent expected. You must indent the code block, and in Python, indentation is a mandatory syntax used to define code blocks inside a function. Now, if you run the file, you won't see the start sequence. Why? Because we defined the button, but we didn't press it yet. We haven't called the function. Come back to section 4 and call start engine right before the GPS block. Run it to see the function in action. There, the engine is started. If we call start engine twice, we see the sequence runs twice. This is the power of functions. We write the startup instruction once, and now Python handles the complex sequence for us whenever we call it. Remember to delete this second call before we move on. So, now that engine is humming, let's check the trip computer. Let's create this calculate fuel function. We will start by making it return none. Now let's make the function smarter. It should take an argument inside the parenthesis. Here the argument is miles. Let's assume the MPG, miles per gallon, of this car is 25. So fuel needed will be miles divided by 25. Replace this none with the variable fuel needed. So this calculate fuel function now takes in miles as an argument, processes it, and returns how many gallons we need. Let's test this. Come to section 4 again. Let's hard code a distance variable as 100. We'll change it later. Call the function and put the distance inside it as the argument. If you run it, you won't see anything in the console. Why? Because we didn't assign the return value to anything yet. So let's assign it to a variable called gallons and print it out. Run it. Success. Trip used 4 gallons of gas. How it worked? This distance value 100 was plugged in the calculate fuel function as miles. Then 100 divided by 25 equals 4, which was assigned as fuel needed inside the function and return. After return, we assigned that value as gallons and printed it. Confused? Okay. To understand better and show you how it works, let's debug the program. Put a red dot here in the distance variable statement. When we debug it, we see the dictionary value in the threads and variable window. Now step over to the next line. We see the distance variable is 100. Now click step into my code to go inside the function. This takes you to the line where we calculate fuel needed. Look carefully at line 20, where we define the function. And here it is showing miles equal 100. The value was passed successfully. Now step into, it takes you to the return statement. And in the thread and variables, we see that fuel needed equals 4. Click step into again, it brings back us to the line 33 again, where we call the calculate fuel. We don't see the gallons variable yet. Now click step over. Here you go. The gallons variable value is 4 now. Step over again and we see the printed output in the console. Now I think you got the picture. What is the workflow of a function? Close the debugging for now. Look at the code, what we did so far. We created a dictionary, then used a function without argument and return to start the engine. Then we used a smarter function to calculate fuel with argument and return option. And then tested it, debugged it for better understanding. Now we have a GPS, an engine, and a fuel calculator. Let's finish the driving logic in section 4. Remember, we said we would change that hard-coded distance variable. Let's ask the user for a destination first. Then we search for this destination in our GPS favorites dictionary. We replace the hard-coded 100 with the value from the dictionary. Run it. Put the destination as home. We see the trip used 0.2 gallons. Run it again with work. We get 0.6 gallons. Now let's properly structure this. Indent the gallons logic and put it inside if block. And add an else block just in case the user types a place we don't know. Run it. If we type shop, it shows error, destination not found. Perfect. Finally, move all the logic inside a new function called drive car and call that function at the bottom in section 5. Test it. Try gym. It is working fine. Now, the line that confuses almost every beginner, if name equals main. Let's break it down with a simple analogy. Imagine your Python file is just a car. Then your functions are the engine of that car. The data is the fuel for that car and your logic is the steering wheel. But the car does not start until you turn the ignition key. And here, this if name equals main is the ignition key. It tells Python only start the engine if this file is being run directly. This prevents the script from auto-starting if someone import your file into another program. So what happens if another file imports this one? Does the engine still start? Let's find out. Now let's open our second file, mechanic.py. In this file, the mechanic imports our CRUD dashboard. If we run it, we see nothing in the console. That means drive car function was not executed. Why? Because it is in the if name equals main logic inside the CRUD dashboard.py. Now the mechanic is here, he wants to start the engine manually. He can call CRUD dashboard.startEngine. Run it and you see the engine start. But usually a mechanic just wants to test a tool. He doesn't want to start the whole car engine. So let's comment out this engine start. Set miles to test equals 100 and call the calculate fuel function directly. Run it and here is our diagnostic report. That's the magic of name equals main. It prevents the car from starting automatically when imported, but still lets us use the tools inside. If we didn't have that line, the entire driving logic would have executed immediately upon import, which is unintended behavior for a module. And that's your complete Python car simulator with a real-world demonstration of how the main block controls your program. You didn't just write your code today. You built a vehicles, a mechanics toolkit, and a professional-grade Python entry point system.
Imagine your Python code running like a smart home. Lights, doors, sensors, all working together. That's object-oriented programming. In this session, we will explore object-oriented programming in Python using a smart home analogy. We are going to master the 4 pillars of object-oriented programming and break it down using one delicious idea. Object-oriented programming is a PI: abstraction, polymorphism, inheritance, and encapsulation. I have posted the code in the description, so for now, just focus on the logic instead of coding along. I'm going to show you the rough draft process that you usually don't see in the final version. I'll be using a Jupyter notebook for quick testing and regular Python file for the final build. If you want to learn how to install Anaconda or create a customized IPY kernel for Jupyter, you can follow the other videos I have linked in the description. But for now, you don't need to worry about anything. Jupyter comes as a built-in option with PyCharm. Open PyCharm, create a Python file called Smart Home. You can also create a Jupyter notebook called Experiment. Split the screen to the right and put the Jupyter notebook there. Now think of your smart home. Every device has a blueprint, actions it can perform, and rules it follows. Now look at this kitchen light. Consider it also has a blueprint, and we can think about a class that is called simple device. We start with the keyword class. This creates our blueprint. Inside, we define a special function called init, a special initializer method. This is the constructor. It runs automatically when you create a new device. We set self.isOn equal false. This word self is crucial. It ensures we are talking about the specific device's data, not all devices. Next, we add a behavior, that is a method, and we call it flip switch. It simply reverses the state. Now we can use this blueprint to create a real-world object. For example, kitchen light equal simple device. That's how we create the object in Python. Now every time we call this flip switch method, it changes the light on or off. Now that you understand how classes and objects work, let's scale up. Instead of one simple device, we want a whole smart home system. Light, speaker, thermostat, all working together. Before writing code, professional developer creates a plan.
And that plan is usually a UML class diagram. You don't need to learn UML in this session, just understand the idea. Look at the box at the top. That is our parent class, smart device. And the boxes at the bottom are the children, smart light, smart speaker, and smart thermostat. This diagram tells us exactly what code to write. Let's slice the pie. A is for abstraction. Abstraction is about hiding complex details and showing only the necessary features. When you use a smart plug, you don't need to know the voltage or Wi-Fi protocol. You just press a button or use voice command. In Python, we use an abstract base class to enforce this. Look at this diagram again. Smart device. This is the parent class and this is our abstract class. That's why you see this A letter before the class name in the UML. Let's import ABC and abstract method from the ABC module. In modern Python development, ABC, which means abstract base classes, is used to create a formal contract between a base class and its subclasses. While you may not have needed it for smaller script, it becomes essential as project scale. Create the class smart device. Notice we put ABC inside the parenthesis. As we mentioned, this stands for abstract base class. We are telling a smart device to inherit all the features from ABC. We are effectively signing a contract with Python that says, this class is just a blueprint. Do not let anyone build a smart device directly from this file. Inside the class, we add init constructor. And this time we are also adding a name parameter. So this will enforce like giving every device a unique identity. For example, if you create a light, you need to mention it as a light, thermostat, and now we need to save it. So we use self.name so that we can save the device name. And we also add two more variables here to save the status of the device. Now let's create a method called connect to Wi-Fi. If you want, you can add disconnect from Wi-Fi also, but for simplicity, I'm just adding the connection function here. Next, we define turn on. For now, I'm just writing pass. And we also add another function called turn off. Right now, turn on is optional. A child class could ignore it if it wanted to. But remember, we also imported abstract method here. So let's put the decorator at abstract method just over the turn on function. This enforces abstraction and it tells us the parent doesn't know how to turn on, but every child must figure it out. Due to ABC being inside the parenthesis of the smart device class, it becomes a blueprint. We told Python, don't let anyone build a smart device directly. Let's see what happens if we try to do that. Let's create an object called light equal smart device light. Remember this name argument inside the initial constructor function? Yes. Due to that, we need to provide a name when we create an object. Run it, and we get a type error saying can't instantiate abstract class smart device without an implementation of abstract method turn on. That's how ABC and abstract method stick to the contract and prevent us from creating an object from the abstract class. How about we create a child class then? We define another class, a smart light, and in the parentheses we put smart devices. For now, write nothing else for this class, just pass. Create the light object. This time instead of smart device class, we will use the smart light class. Run it. We get the type error again because this smart light didn't create the turn on function. This actually was enforced by the decorator abstract method. Let's add the turn on function for a smart light. Run it again, and this time we don't get any error. Call the turn on function. Run it. Oh, it's working.
Check the turn off function. Both are working fine. This is the abstraction of object-oriented programming. How about another pillar of object-oriented programming? I for inheritance. Look at this SmartLight class again. Did we write any code for turn off or connect to Wi-Fi inside the SmartLight? Or how about the name? We put light inside the SmartLight when we created the object, but there is no name variable inside the SmartLight class. So all the variables come from the abstract class, SmartDevice. We can say these variables are shared attribute. These methods are also related to inheritance. So let's put a comment inheritance here in the SmartLight class. In the UML, SmartDevice is our abstract class. And for the subclass, we created SmartLight. In the base class, we didn't create a fully operational turn on method. So we created that in the child class. Let's see the demo. Call the connect to Wi-Fi function and put the argument myhome5g inside the function. Run it and we see that it is connected to the Wi-Fi. Now imagine if you had to write the code connected to Wi-Fi from scratch for every single new gadget you bought. This is a waste of time and violation of the DRY principle. That means don't repeat yourself. In our smart device base class, we write the connect to Wi-Fi logic once. Later, when we create a smart light, it inherits the ability automatically. It gets the Wi-Fi code for free without us typing it again. So if you look closely at the sidebar in PyCharm, you will see this little icon next to our class. That tells us smart light is a child of smart device. We didn't write the Wi-Fi code here, but PyCharm knows it's there because of inheritance. Create the smart speaker in a similar way. Create the object from it, connect it to the same Wi-Fi, run it. So both the light and speaker devices are created and connected to the Wi-Fi. As we have discussed inheritance, that leads us to P for polymorphism. Poly means many, morph means forms. So look at our turn on method. For a light, turning on means glowing. For a speaker, turning on means playing music. Polymorphism allows our main system to treat all the devices exactly the same. How? Let's put the light and the speaker inside a list called devices. Loop through the list and call the same method turn on. They each know exactly what to do. And now look at the output. The light is glowing and the speaker is playing your favorite playlist. So far, we have discussed about abstraction, inheritance, and polymorphism. Finally, let's focus on E for encapsulation. This is about protection. You don't want a guest in your house accidentally resetting your device's firmware or changing the voltage to unsafe level. So let's create a smart thermostat. Here, inside the init method, we at first call this super init method to make sure the parent setup runs. Then we define extra variable that is self dot double underscore temperature. Notice these two underscores? Yes, in Python we encapsulate data by making it private and usually by adding two underscores before the variable name. So this restricts direct access. You cannot access it directly from outside the class. So we use getters and setters to control how that data is changed. To allow the safe change, we write a setter method called setTemperature. Here we add logic. If new temperature is greater than 60 or less than 80, that times we allow to change the temperature. So this ensures new temperature can only change the setting if it respects the logic here. The getter method is simple. We are just returning the private variables temperature. Look at the UML one more time. Look at the thermostat. Do you see this minus sign here? next to the temperature. In UML, a minus sign means private, and with that we have finished this whole diagram. Let's test this thermostat also. Create it, connect it to Wi-Fi, and add it to the devices list. Run it. Perfect. Now let's test the encapsulation. We will have three types of test here: safe change, unsafe change, direct access attempt. For the safe change, we tried a new temperature of 75 degree, which is in the range of 60 to 80. So it allows us to change the temperature. But for the unsafe change, when we tried 500 degree in the main block, the logic rejected it. So we are protecting the data from bad input. For direct access, let's use a try and accept block for the test. So when we try to print the private variable directly, it throws an attribute error. As we have checked all of this, let's put this whole block of code inside the if name equal main block so that we can import this smart home script as a module in other programs. You have just finished your whole smart home project and learned object-oriented programming in Python. So next time when you are coding, remember API. Abstraction hides the mess, polymorphism lets different objects respond to the same command, inheritance prevents you from repeating code, and encapsulation protects your data. In this session, we are going to build a complete data pipeline. We will fetch real data from the internet, clean it up into a data frame, analyze it with Pandas, and finally visualize it using matplotlib. This is the essential workflow used in real data projects, and by the end of this video, you will know how to do it end to end. For our data source, we are going to use JSON placeholder. If you have not seen this before, don't worry. This is completely safe and free API created by Typicode, especially for developers to practice with. You can see right here on their homepage. It says free, fake, and reliable API for testing and prototyping. It simulates a real database but contains only fake dummy data. None of these people are real, so we don't have to worry about privacy or security while we learn. For example, look at this post data. Now, we are going to grab this list of 10 users, which includes their name, username, email, address, and company details. Look at this structure. See how address and company are the nested dictionary with more information. If we don't handle this right, our analysis will fail. You can also look at the raw data and header here. I am viewing this in Firefox because it automatically formats the JSON into this clean tree structure and making it easier to read than other browser. Let's start coding. Open your PyCharm project, right-click the folder and create a new Python file named generate CSV. First, we need the request library to talk to the internet. Notice the red squiggly line under the word requests. It is saying no modules name request. We can simply click the red light bulb icon and select install package request to fix this instantly. Now let's set the URL and send a GET request. When we call .json method on this response, it converts that raw data into a Python list of dictionaries, basically a folder full of mini profiles. Let's do a quick print test to make sure it works. Perfect. The data matches exactly what we saw in the browser. Now if we just want to pick the name from the first data, just write name here after the index. Next, we need to save this data. So we import Pandas. Again, we see the red arrow line. This time, let's install it differently. Open the terminal tab at the bottom and type pip install pandas. This is the standard command line way to install libraries. Let's create a data frame the standard way using pd.dataframe_data and save it to a CSV file. Before running the script, notice that the file does not exist in our project. Run it and we get the CSV file user report nested here. Open it in PyCharm. Look at this address and company column. We see more data in the cell in the curly parentheses like dictionaries. So these are nested data, and you can also open this file in the Explorer, and from there you can open it in the Excel. We can easily fix the issue with the nested data. Last time we used standard method, that is pd.dataframe_data. That's why Pandas kept the dictionaries intact inside the cells. But this time, instead of using the standard method, we use pd.jsonnormalize. It detects nested dictionaries and explores them into separate columns using dot notation. Let's save it as another file and run it. Now look at the old file and the new file. The issue has been fixed. You can open it in the Excel also. So the nested dictionaries have been exploded into separate columns using this dot notation. Now that we have learned how to fetch the data from the internet and save it, let's focus on the data analysis. Right-click project folder, select New, Jupyter Notebook, and name it Analysis. Split the screen. Let's copy the code from the generate_csv.py file. Run the cell by typing Shift Enter. This time we will use the flattened data, so we use JSON normalize. Let's look at the data frame. Type df and run it. You can see the whole data frame of 10 users here. But it is not a good practice when you have thousands of users. With large dataset, you should use df.head to see just the first 5 rows. You can also pass a number like 1 to see just a single row. If we want to see just one column, for example, the company catchphrases, type the column name inside the square bracket, and now we can see all the values of that column. Let's do some feature engineering. I want to know who has the longest company catchphrase. We can create a new column called phraseLen that calculates the character count for each phrase. You can see the new column added right at the end. To keep the output clean, we printed only name, catchphrase, and the new length column. For a quick statistical summary, we use df.describe. This instantly shows us the average length, the minimum, maximum, and other values. We can filter the data. If I only want to find Chelsea Dietrich, I can use a simple Boolean filter. It will only fetch the Chelsea Dietrich's data if it finds the match in the name column. Let's try the filter for phrase length also. Try it for the catchphrase shorter than 30. We get just one result. But if we bump that to 35, we get 6 users. Look at the original data frame once more. Now let's sort the entire data frame by our new phraseLen column in descending order. We can see the rows have been sorted based on the phrase length. Compare it with the old one. If we run, we don't see the old data frame. Why? Jupyter cell only print the last variable in the cell if we don't put print. So put the print command here. Now we can see the both data frames. We can also group the data. Let's group by city. Since every user in this dummy dataset lives in a different city, the count is just 1 for every city. But in real data, this would show you where your users are concentrated. So far, all of our analysis was based on numbers. How about the visualization? For that, we need matplotlib library. We have installed libraries via the light bulb and the terminal. But this time, let's run pip install matplotlib directly inside a notebook cell. This is a handy trick if you don't want to leave Jupyter. Once installed, import it, set a plot style, and define a figure size. Let's create a bar plot. I will put the username on the x-axis and their phrase length on the y-axis. Run it. We get the plot, but it's a bit messy. Let's refine it. Change the color. Still, x-axis is messy. Rotate the x-sticks by 45 degrees. Now looks good. Put title and the labels. We got our final bar plot.
By changing little bit, we can get a line plot. Copy the code in another cell. Instead of bar, use plot. Run it. It changed to line plot. Add marker and line style. Here you go. You got a nice line plot. Please remember to comment the pip install matplotlib line. You only need it if it is not installed in your environment. Once your library is installed, you should comment out. Otherwise, it will try to install every time you run the notebook. And that's the full workflow. We fetch the real data, save it to a CSV file, cleaned it, analyzed it, and finally visualize it. This is the foundation of almost every data project you will build in the future.
In this session, we are going to move our code from our local machine to GitHub, the world's leading platform for developers to host, share, and collaborate on software. I will show you how to connect PyCharm to GitHub for the first time, even if Git is not installed yet. And then I will show you how to sync everything properly. If you don't have an account yet, you can sign up at github.com by entering your email and following the prompts. Now let's head to PyCharm. You can select Share Project on GitHub from the VCS menu at the top or from the VCS panel in the bottom right. In the Share Project on GitHub window, let's change the repository name from Python Project to Python Quick Start. We will make this public so others can see our work and a brief description below. In the Share By box, if this is your first time, it will be empty. Click Add Account and select Login via GitHub. These open your browser where JetBrains will ask for permissions. Click Authorize in GitHub. Sign in to your account and you will see a message saying you have been successfully authorized. Now you can close the JetBrains page and refresh your GitHub page. You will see that you are logged in and ready to go. You can create a repository directly on GitHub, but this time we are doing it through PyCharm. So let's go back to PyCharm. Now you will see your GitHub account listed in the Share By box. Click Share. Since Git is not installed on this computer yet, PyCharm will show error in the bottom right. Don't worry, just click Download and Install. And while that runs in the background, if you check your GitHub browser, you will see the repository has already been created, even though it's empty for now. Once the installation finishes, the VCS panel in the left bottom will confirm Git has been installed. Click VCS in the top menu and select Enable Version Control Integration. The pop-up window will ask you to select a version control system. Choose Git. As soon as you click, the VCS in the top menu will changes to Git. Now PyCharm activates Git tracking. Your files may appear brown or red depending on the theme. This simply means these files are unversioned and not committed yet. You can click Commit from the top menu or from the left panel. Select your files. Don't click Amend as this is our first initial commit. Write a message and click Commit and Push. When you push, PyCharm uses your GitHub profile, and this can be different from the repository owner. That's how multiple collaborators can work together. For now, I am using the same profile, and you can set the properties globally, but I would like to keep this profile only for this project. That's why I unchecked it. In the push window, make sure the remote URL is correct for the master branch. Click the Define Remote, put the URL of your repository. Click OK. Now you see all the committed files are here. Hit Push. Go back to your browser and refresh. Your Python scripts are now live for the world to see. To make this professional, we need a front page. On the GitHub website, click Add README. Type a quick summary, check the preview, commit the changes. In the commit window, write a short description and commit the change. You can see the newly created README file in the repository now. Come back to PyCharm. To bring that README file from the web to your computer, click the Update project. The README file appears instantly in your project folder. Open the README in PyCharm, make an update, commit the change, push it to GitHub. Refresh the GitHub page again, and you will see the updated README instantly. Your PyCharm and GitHub are now fully connected and in sync.
Congratulations! You made it to the end of the Python fast track. You took 35 Python core concepts and turned them into 6 practical applications. Now that your code is live on GitHub, that shows you didn't just watch a tutorial, you actually build the applications. If you want to review the code later, I have put the direct link to this complete source code and the printable cheat sheet in the description below. If this Python fast track helped you, hit subscribe. I will see you in the next build. Thank you for watching. Happy coding.